So I'm going to let you read this part, and if you want to have it explained to you in a little bit better depth, you can go watch the Mr. Leckie video, or certainly you can go find something on YouTube. The big idea is the Riemann sum is when you take these rectangle area approximations and you go to an infinite number of rectangles, and that's what this is called, or trapezoids or whatever, but usually it's rectangles. That's what Georg Riemann talked about. So the one thing I'm going to ask you to do is, how do you take a Riemann sum expression like this and write it and as an integral, as a definite integral, and we're going to learn about the notation of that on the next page. So we'll hold this, keep that on hold. What I do want you to see is the function we're dealing with is x cubed. That's telling me as I get more and more rectangles, that width, the change in the width, and this is how I get the height. That's the f of c. Okay. So what does a definite integral mean? Well, if you look on page 77 or 277 in the textbook, you're going to see some additional notation on how to interpret what the heck all this means. And it's pretty easy. The integral signs mean you're going to find the sum of all the rectangles you're finding. You let it go to an infinite number of rectangles, and this is the function. This is the function that we're integrating. And then you have the dx, means you're letting those rectangles go to an infinitely skinny rectangle. So basically we get all those solid lines when we fill in the area. And remember when you do the R-sum program, how when you pick like 1,000 rectangles, how the shading looks all solid. You're saying you're going to a very skinny rectangle. Let's fill them in. And then these are the left, that's the left end of the area you're trying to find. That's the right end of the area you're trying to find. And then we usually have these left, the lowest number on the left, the highest number on the right. And you'll see more of that in the next section. So that's what that symbol means. So now, one thing we're going to ask you to do is to be able to take this Riemann sum notation and write it as a definite integral. So a couple of easy things to know, or if you think about the sum, sigma is the sum, we're going to write the sum integral symbol, and here's our left end is 2, and our right end is 5. So once you've got the bound set, then you wanted to ask yourself, well, what function am I working with? And for this one, I've got something being cubed. So the function I'm cubing, some function I want to give me the height of the rectangle is x cubed. And then you're going to have the width of your rectangle, and we call that dx because it's the delta x. And I believe that's it. So that's my definite integral based on that Riemann sum. So now that you understand what this integral notation means, I'm looking at this, and this is telling me, hey, I want to find the area under the curve y equals 3, not much of a curve, from 2 to 9. And then just like what you did back in 5.1, we're finding the area of that rectangle. Well, that rectangle has a width of 7, or a length of 7, and a height of 3, or a width of 3, so 3 times 7 is 21 square units. Okay? Then we're going to look at this one, and let's see, so I'm going to graph an absolute value function, and I'm going to find the area under that curve and between that curve and the x-axis, as I guess what I should be saying, from -2 to +1. And what I'm seeing here is a triangle here on the left and a triangle here on the right. And to get that area, I see that this triangle is 2, and I know the absolute value of -2 is 2. And this width is 1, or base is 1, and absolute value of 1 is 1. So I've got two triangles, 1/2 times 2 times 2, because it's 1/2 times BH, right? So 1/2 times the base times the height. And then the same thing on this other side, 1/2 times 1 times 1. And so that's what that cancels out. So that gives me 2 times 1/2, or 2 plus 1/2, so 2.5 or 5/2 would be that area. Now for this last one, which I'm hoping you've seen this enough times that you recognize that the function we're dealing with is a semicircle that's above the x-axis. And that semicircle has a radius of 3 because the square root of 9 is 3. 1, 2, 3. Okay, so that's the area we're looking for right here. So the radius is 3, so all I really need to do is do pi r squared and then cut it in half. So 9 over 2 pi, or 9 pi over 2, will be the area of that semicircle. So what Dr. Leckie is trying to get at here is when you have an area below the x-axis, that's a negative area. So here's this equation, the graph of y equals, this is just negative x plus 3, right? So I found the y-intercept at 3 and went down 1 over 1. So the area between the curve, and the x-axis, between 4 and 8. Well, if you think about it, here's x equals 4, and x equals 8. I'm going to kind of run out of room. And this is a area that's below the x-axis. So that's going to be a trapezoid. And so what we need to figure out is, let's see, we know that this is 4 to 8, so that's a distance of 4. That's the height of the trapezoid. This will be, let's see, what do we got? We function 3 minus x. Well, if this is 4 and this is 8, 3 minus 4 is 1, so negative 1. And 3 minus 8 is negative 5. So I'm going to do, let's see, it's 1/2 times the height, which is 4. Remember, the height is this distance here, times base 1 plus base 2, and we can leave the negatives right in here for this case. So that's going to be 2 times negative 6, which is negative 12. So we just evaluated this integral. I found the area in that curve on that range, which is just that negative area. So now we're doing some things where they've given us the value of a definite integral. And what we want to think about is, what the heck does the sine graph look like on those range? So now you got to dust off your pre-calc trig graphing skills. So that's 2 pi, that's pi. Why did I stop at 2 pi? And I'll let you think about that before I say anything. Let's see. Because the period is 2 pi for a regular sine graph, right? So halfway around would be pi. Pi over 2, 3 pi over 2. And looking ahead here, I see I got to go from use negative pi, so I'm just going to label those backwards right now. Okay, then if I graph this, it looks something like this. And going backwards, it looks something like this. And they told me that this area here is equal to 2, from 0 to pi, so that's 2. So if they're asking me to find the area from pi to 2 pi, that's this area here, right? And that's below the x-axis, so that answer is negative 2. Then they want me to go from 0 to 2 pi. Well, I've got a positive 2 and I've got a negative 2. Those are going to cancel out, so that area is 0. From negative pi to positive pi, well, again, I've got this area here. That's below the x-axis. I know it's 2, so it's negative 2, and that's going to cancel out and give me 0, because I'm going from negative pi, which is that negative 2, up to positive pi. Well, that area is positive 2. And then what's happening here? Well, so for part E here, let's figure. I have the sine graph shifted up 2 units. So 1, 2, and 0. And I'm going to stop at pi because they're telling me to find the area from 0 to pi. And the amplitude is 1. So I'm going to look at that part of the sine graph. And we know that this area is 2 because they told us that. And I know that this area here forms a rectangle. And that rectangle is pi by 2 high, right? Because that's the line y equals 2. So pi times 2 is 2 pi. So the area for part E, that integral, works out to be 2 plus 2 pi. Now I'm realizing that I missed question C, so I'm going to do that one quickly. So I know from 0 to pi, that area is equal to 2, but they're only asking me from 0 to 2 pi. And if you notice that that is symmetric, right, that cuts that region in half, so that area is going to be 1. So this is one of the things you can use your calculator for on the AP tests. In fact, this is the last thing you're going to be able to use your calculator for in the AP test, which is we know how to graph a function. You can find the zeros, solve a function. You can use n-deriv, calculate the derivative at a point. You can also calculate the area of a definite integral with your calculator. And all you have to do is show the initial setup. I mean, you would have to write something like this, and then you can just state the answer, if it's a calculated portion. So what I've done here is I've grabbed, if you press Math 9, that gives you this FN int feature, and then if you get your calculator set up in Math Print version, you're going to get this. You're going to have a bunch of a square here, a square here, a square here, and a square here. So what you do is you just type in, -1 is our lower bound, 3 is our upper bound or right side. You type in the function, and then you're going to tell it you're taking the derivative with respect to x. You can play around. I never do this too much, but you could play around and use t's here and then put t here, and it should do the same calculation. If your calculator's not in Math Print, or if you get an 83, what you're going to get is you're going to get the FN int without the integral symbol, and the syntax for this is, right here, it's listed right there. You're going to write your function in, then you got to put comma x, and then you got to put comma the lower bound. Notice I use 3, and then upper bound, or 1, and then upper bound I use 3. Give you the same answers. The other cool thing about it is you can put your function in y1, and you can have it do the same thing with y1 by doing that second vars, y vars. Okay, and this will calculate the area for you. It's very cool. So why don't you go ahead and get those answers, and I'll check it, and then I'll show you and try setting this up. Oh, maybe we should do this one. I'll set that one up. Let me get the answer here, and I'll come back with a setup for this next one. So I calculated, hit one of the calculators, and I came up with 4 2/3 for the area under that curve, or between the x-axis and that curve. And then to set up this next one, I typed it in just like I saw it. 3 plus 2 times the integral from 0 to pi over 3 of tan x dx. Okay, and that did it. And you hit enter, you'd get the answer. I'll probably show you this next part in class, so I won't make you do that right now. So, well, I hope this helps you get started.